Welcome back for the last part of this tutorial. And in this part actually we're going to cover everything, or not everything, but a large part of stuff that we have not covered. And this will allow us to give some conclusion and to give some outlook about possible future research or future project on network clustering. A first thing that was not covered is non-homogeneous model. And by that I mean that starting the section 3 on SBM, we assume that you have a probability P of interaction inside a block and Q across block, but you could assume that between different blocks the probability of interaction will be really different, right? And so this is what we call non-homogeneous, and as we say, we can also study SBM with more general interaction than just binary. So the most general model we could look is we have pairwise interaction xij, and if I have a node in cluster A and a node in cluster B, its interaction will be sampled from a probability distribution FAB. So that will be a non-homogeneous SBM, and I have a set of FAB that tells me how am I going to interact between block A and block B. Another thing that I can add is some node attributes. What are node attributes? You can think of, for every node, you have a vector, yi, let's say, a feature vector. So for example, on a social network, for every node you may know the name of the people that Daniel covered, like name Brazilian versus French. This could be used for clustering. You could know its age, you could know some biography, some words present in biography, and so on. And this can be represented as some random variable yi, and we can assume that if you are in cluster A, your attribute yi will be sampled from a distribution HA. And that leads rise to a model, a non-homogeneous model for the graph interaction, where you also have node attributes. And on this model, we can ask the same question as we ask: can we recover the cluster, recover the membership Z? And of course, we have two types of intervention. We have the intervention from the network, and we have the information from the attributes. So maybe only looking at the attributes will already give you enough information. You could recover the communities, or maybe only looking at the networks could recover the communities very well. Or in some setting, combination of two actually will recover. And it turns out that the key quantity to look at is this, that is given in equation 4.1, and indeed has two different types of information. You have one term which is information from the network, and another term which is information from the attributes. So that's and one example you could look at, for example, to make it more concrete, is to assume that you have a binary network. So the interaction between a block L and a block L prime is Bernoulli distributed, with A log n over n if you are in the same block and B log n over n otherwise. So that's just to go back to a homogeneous setting, because we covered that quite extensively in section 3. And we could assume that on the attribute we have some Gaussian attributes. So if you are in block L, then your attribute will be sampled from a Gaussian distribution with scale. So we assume that the mean is mu L times log n, and the variance is simply sigma squared times identity. And the quantity delta that we defined in the previous slide, in that case can be written as, so you have log n over n, which is scaling factor, time two terms. And actually the nice thing of this is the first term, the square root of a minus square root of b squared divided by k, is the term, exactly the term that you would get if you don't have the attributes. If you throw away the attributes, this is the information theoretic quantity that you get. But because you have the attributes, you have the second term here, which is a minimum separation between the center of your Gaussian. So you have minimum here between A, or pair of cluster AB, and you get mu I minus mu B, the square of the Euclidean norm, divided by 8 times sigma square. So in a sense, this is a signal to noise ratio, which tells you from the attributes how much information you will be able to gain by looking at the attributes. And you combine these two, and you get the amount of information you get by looking both at the network and attributes at the same time. Another thing that we can derive from this previous thing is what happens if I have no attributes. So either I have no attributes, or the probability distribution for every attribute is the same, no matter which cluster I have. And if I consider again a binary graph, so F, the probability of interaction between block L and L prime, in that case will be Bernoulli, but I'm assuming I have some coefficient alpha LL prime times log n over n, and then we can show that this quantity delta recover quantities that we call the Chernoff-Hellinger divergence for and that appear for clustering non-homogeneous SBM. So this gives rise to extension of the SBM in a non-homogeneous setting, or a setting where you have attributes, and the attributes could be, in this example, they are Gaussian, but you could also think about other distribution for your attributes. Another thing we haven't covered is degree corrected extension of SBM, and the reason for that is one big issue with SBM is that if you look at a node, they all have the same degree distribution, or at least nodes that are in the same communities have the same degree distribution, and this is not realistic because when we observe graphs, almost always what you have is you have some nodes that are very high degree, some nodes that are lower degree. For example, in transportation networks, you have some cities that act as hubs, and a lot of if you have a train, like a lot of train may go to the city and so on. If you have a social network, some people act as influencers. They also have a very large degree, and this can't be a model by the SBM, but we can propose a very simple extension of the SBM where, in addition to have the cluster label Z1 ZK, this vector Z, we have also some degree correction parameters, which is just n quantity theta 1 theta n for each vertex, and then the probability of having an interaction between node I and j is going to be theta ij times p if you're in the same community, and theta ij times q if you're not in the same community. Here in the formula I put a minimum just to make sure that probability is smaller than 1. And what means this parameter is if I have a node I which has a high theta I, it means this node will tend to make more interaction, right? Because the probability of interaction, here I get a multiplicative coefficient theta I in front of either the p or the cube. And in contrast, if I have a node which is a small theta I, it will tend to have less interactions. And we can ask the same question, like what's the min-max rate on this model? And this was answered a few hours ago. There are some technical conditions that I'm not showing here because it's not necessarily interesting, but the min-max rate, and again, not necessarily surprisingly, we get two different rates whether we have two communities or more than 3 communities. And the rates here are a bit more complex, but because they have to involve the fact that every node are not the same, right? So if you have a node with a high theta I, then it may be easier to recover it because it has a lot more connections than the nodes that have a small theta I. So that's for extension on degree corrected extension. Another nice extension that became popular recently are geometric extension of stochastic block model. And so here, I'm assuming again that I have cluster labels. So let's say Z1, ZA, and let's suppose that I have only 2 clusters, and I have probability 1/2 to be in cluster 1, 1/2 to be in cluster 2. I'm going to assume as well that I have some geometric label. So here some random variable x1, xn, which are distributed on the sphere SD-1, sphere of RD, a multi-dimensional space, and I'm going to generate the graph as follows. So the probability to have an interaction between node I and j, given the position of I and j, xi, xj, and the cluster of I and j, is equal to 0 if the two nodes are too far away from each other. So I have a threshold tau. If the two nodes at L2 distance, for example, between the position xi minus xj is larger than tau, then no way I'm interacting. So I'm not going to interact with people that are far away in the geometric space. And if I'm a distance less than tau, I'm going to interact between I and j with probability p if I'm in the same community, and with probability q if I'm in a different community. There are several variations of this model that will not cover here, but this is the general idea. And we can lay down some recovery results. For example, when can I get exact recovery, when can recover the cluster labels, that was an head, for example. And actually most recent work assumes that the geometric labels are known. So you know x1, xn, and you know as well the graph, and you want to recover z, the partition. If the geometric labels are unknown, this is vastly is still open. And an interesting observation that we can do is some algorithms that are known to work for SBM will fail completely on this geometric model. And for example, spectral clustering will fail. And the reason for that is spectral clustering will tend to find a cut or like a partition that's associated with the geometric position of the node and not with the cluster labels of the nodes. And that's why this makes this problem quite interesting, because some algorithms that may succeed very well on stochastic block model, they may actually fail on geometric block model. Another interesting setting, especially in the realm of machine learning, is semi-supervised community detection. And what is that? So we were looking at the unsupervised problem, that is, we just observe the graph and we want to recover the clusters. But we could also assume that some oracle reveals some the community label of some nodes. Like for a small portion of nodes, maybe 1% or 5% of nodes, I know the community labels, and I want to infer based on the information of the arc and the graph, I want to infer the community labels of the other nodes. And of course, I can assume that the arc is perfect. So the arc really, all the community labels that are all correct or noisy. Like the community labels revealed some of them are wrong, some of them are correct. And already quite large amount of algorithms are proposed. One class of algorithm is to propagate the label. So I have the graph, I have the label for some nodes, and the nodes that are already labeled by the arc, I will make them propagate their label to their neighbor and the next neighbor and so on. And various ways of propagating give rise to different kind of algorithms. So label propagation, label spreading, Poisson learning also more recently proposed. So that's one class of algorithm. Another class is, for example, to look at spectral clustering and make a constrained version of that. To say, okay, I want spectral clustering, but I want the output of spectral clustering to agree with the arc. So I either agree perfectly, if I'm sure that the arc is perfect, but if I know that the arc is noisy, I may want to agree, but to let the algorithm also possibly change the label of the node that are labeled by the arc. So there are several versions also of constrained spectral clustering. And the last, for example, class of algorithm that Daniel slightly covered as well is graph neural networks. And actually it really makes sense for graph neural networks in this semi-supervised setting, because I can learn and I can minimize some loss function because I have a part of my data that is labeled, right? And some interesting fact is that if you take a real network and you compare, for example, an unsupervised clustering algorithm, let's say spectral clustering, versus a semi-supervised clustering algorithm, let's say Poisson learning or GNN, you will find that the semi-supervised very often perform much better. Right? It's an observation that we can make empirically. So even when you reveal a small amount of labels, it tends to help a lot in the problem of community recovery. So that's actually nice, and so it means, okay, let's study this. It seems very appealing. But it has been shown that in SBM, actually, if you reveal even a constant fraction, so not full, but just a constant fraction of nodes, actually it does not change the threshold for exact recovery. And that means that SBM is not necessarily a good model to study the semi-supervised learning, or at least we can't really explain with SBM why on regraph we see so much difference between unsupervised and supervised, semi-supervised. In SBM, actually, and even the arc reveals some fraction of nodes that doesn't help. And the high-level intuition of that is we show that in SBM the best error rate that you can achieve, it was given by this problem where somebody revealed all the vertex except one, right? And you had only to reveal one vertex, which means that if you have the graph plus an arc that reveals the vertex, it's not going to change actually the error rate, because the error rate is obtained by exactly the problem of looking at what my error in the setting where I have only one node to classify. So that's interesting and could lead to nice future work on semi-supervised learning on the graph. And so let's now wrap up a bit everything by giving some final summary. What have we seen in this tutorial? So first we have seen the question how to detect network cluster, and this Daniel explained different algorithmic approaches to cluster networks. Another question we tackle was when network can be identified, and here we show some different information theoretic criteria, for example for recovery or exact recovery or optimal rate of recovery. And last section we saw some variation of modern network clustering. We show different model, and all of this is always motivated by different applications, right? If you have an application where you have graph plus some attributes, then you may want to model it as an SBM with node attributes. If you're in semi-supervised learning, you may want to study that as well, and so on. And of course, there's much more information that hasn't been covered in this tutorial, and we give in the appendix, and you will have access to the slide, we give some reference to textbooks, to survey papers, and even research papers. So thank you very much for attending and listening to this tutorial, and good luck for clustering networks in your life.